So first of all, I want to thank Yafen Ban for inviting me. I am really excited about what I can learn from all the wonderful speakers today. And I'm also excited to talk to you about our real-world neuroscience research. So especially before the pandemic, but probably still true, most of us interact with others face-to-face on a daily basis. But we know very little about how the human brain supports everyday social communication, let alone outside laboratory environments, whether it be in person or virtually. Because for decades, we've used a laboratory model of human cognition where we assume that the same perceptual mechanisms apply to the lab as they do to the real world, but we don't actually often test this model. And so we've proposed a model where the lab studies and real world studies enter into an exploration-confirmation dialogue with one another. And today I'm going to illustrate our approach to conduct real-world neuroscience research by building relationships with artists, scientists, and educators in a series of hyperscanning studies where many of them we leverage hyperscanning neurofeedback to engage the general public in scientific studies. And so concretely, a few years ago, Matthias Oosterich and I started developing tools that allowed us to record data from multiple people simultaneously and translate interbrain synchrony into different types of output, like the extent to which two heads merge in and out of each other. Now here we see a neurofeedback game where dyads can try to sync up their brainwaves as much as possible, and then after 3 minutes, they can compare their synchrony score to the score of the pairs that went before or after them. Or they can try out different conditions within a dyad, like looking at each other, looking away, singing a song, playing a game. And so we are now streamlining this neurofeedback software for public use in the Rhythms of Relating projects, and we've used it, and it's proven very valuable for scientific outreach in science museums and festivals, and it has allowed us to test the viability of collecting data under more naturalistic circumstances. Another example is Compatibility Racer, where synchrony is translated into the motor speed of a card that speeds up as synchrony increases and then slows down as it decreases, metaphorically fueling the compatibility racer with human connectiveness. So as you can imagine, it's not very difficult to find people who want to participate in these kinds of studies, but you can also see that they treat it as an amusement ride, moving their bodies and laughing, and that renders the EEG data fairly unusable. So in the mutual wave machine, we try to be more mindful of motion artifacts, asking people to engage in face-to-face interaction for about 10 minutes inside an intimate capsule where they're completely immersed in light patterns reflecting their brain synchrony. And their more light reflects the enthusiasm or exhilaration you're connecting to somebody, whereas a lack of synchrony turns the capsule dark and lonely. And then in some versions of the installation, people also see a real-time video image of themselves emerge behind the person in front of them. And this alludes to questions of what it means to synchronize to another person. Are you really seeing the other person? Or are you merely projecting a mirror image of yourself onto the person in front of you? Now, about 5,000 people have participated in the mutual wave machine across Europe and the US. And today I'm going to focus on the most comprehensive and well-controlled data set, which is recorded in 2016 in Athens. And here half the people were explicitly told that more light meant more brain synchrony, and half of the dyads were not given this information. And so we hypothesized that this would motivate people to focus on their social interaction and as such maybe increase interbrain synchrony. And we also asked pairs about their social closeness, their personality traits, and their mental states. And so here clearly we're still dealing with less than suboptimal recording conditions, which we tried to offset by collecting data from tons and tons of participants, and then also allowing us to throw away data from tons and tons of participants if their data quality wasn't up to standards. And we used connectivity metrics, and this was led by Yorgos Michalareas, that remove the common signal or the common noise in our case. And we find that those pairs who are closer to each other also report higher, have higher social closeness and higher overall synchrony. And the same was true for pairs with lower personal distress, possibly because they were less self-oriented. And then we saw that there were also changes over time in synchrony, specifically those pairs who remained more focused also showed more synchrony in the second half of their experience. And the same was true for the neurofeedback group. So those people that were told that the light related directly to their social interaction also showed an increase in synchrony. And what's important to note is that we didn't see this as a function of whether the feedback was real or sham, by which I mean that it really seems to be the motivation. So believing that what you're seeing relates to your social interaction makes you focus on your social interaction and thereby increase synchrony. Now, all our projects have a scientific and an artistic component, as I've illustrated, but they also have an educational side. So we show people their brainwaves, immediately making it obvious that we're not dealing with a straight-up mind-reading device. And we can inform people about reverse inference, right? So you cannot use EEG synchrony to give people advice about whether they should get married or divorced, at least not in the current state of affairs. And we expanded our educational side of things further into the classroom and by beginning to study group synchrony as opposed to dyads. Now, the classroom is a highly social environment, which I am sure I don't have to convince you of. But what is interesting is that it also is usefully similar to the lab in certain ways. So for example, both students and laboratory participants are used to engaging in a set of predetermined activities for a few minutes. Now you do this, and now you do that. And students are used to being told to sit still and shut up, which is great for data quality. Now, concretely, we basically took over 2 biology classes in 2 different high schools in New York City. And we started the school year with a crash course in neuroscience and scientific design, taught kids how to use the equipment, and involved them in the experimental design of the study that they were then going to be participants in. Which involved us recording EEG data from them throughout the school year while they were engaging in their regular class materials. So we had 2 schools and 12 students and a teacher in each class, and then we recorded during multiple classes where instruction activities were repeated as well as baseline conditions. And then we asked whether brain-to-brain synchrony during their regular classes was related to classroom engagement and classroom social dynamics. So, for example, we asked kids after each class how much they enjoyed each teaching style or activity, and perhaps unsurprisingly, kids were into videos and into discussions, but not so much into straight-up lectures. But what is interesting is that we saw that this pattern was reflected in interbrain synchrony, where kids showed more synchrony for videos and discussion sessions than for lectures. And interbrain synchrony during class was also predicted by classroom social dynamics, how much they liked the teacher and how much they liked each other, by their focus, and by social traits. So some kids are more comfortable in groups than others, and that predicted their synchrony during class. And similarly, replicating the mutual wave machine results, we saw that personal distress was inversely related to synchrony, where those kids that were less personally distressed were more synchronized with the group. And so we see that there is a number of factors that each predict interbrain synchrony, which in the classroom case was measured by coherence. And what would be really nice, of course, is if there's some unifying mechanism that explains why all these factors predict coherence between people. And so from the classroom perspective, shared attention is a very likely shared construct, so to speak, between all these factors. But attention is obviously not a very useful construct because it's vague and broad. What might be more useful is to start thinking about what we actually bring to the table when we're engaging in a social interaction or when we're engaging with the world, period. So each of us bring personality traits, factors relating to the neural architecture, our mental states, are we happy or sad, and priors, belief systems about the current situation, but also predictions about syntactic structure and words based on our statistical knowledge. And we know that similarities or dissimilarities in these different factors between people can already explain interbrain synchrony even in the absence of an actual social interaction, right? And we see that if there is a stimulus, which could range from tones to videos, people don't actually need to socially interact with each other to synchronize their brainwaves or not, again, depending on the interaction of all these individual factors. But what we're interested in our case specifically, of course, is how social behavior like language or motion or gaze might act as interaction-dependent synchronizers by which you can establish a common ground and interbrain synchrony and possibly social closeness as a consequence. So to illustrate this with the data that we've seen, so the teacher's speech, like the lecture or group discussion leading, is a exogenous synchronizer with a temporal structure. And then kids' brain activity, if they're not engaged, is also not going to entrain with the teacher's speech and thereby not going to synchronize with each other. In the ideal world of the teacher, of course, there is a perfect relationship between the student's brain activity and the teacher because it means that they're perfectly engaged and trained to their speech and might thereby learn more. But in the real world, of course, there's variation, just like right now. Some of you might be listening to me very tightly and train with my speech, while others might be more distracted and not be super attentive to what I'm telling you. And so this illustrates how, by studying real-world social interactions and thinking about the richness and decomposing its richness into different tasks and different social structures can actually get you pretty far in trying to get at the mechanisms that support social dynamics, even though we're not dealing with controlled experiments. So I've shown you some data from classrooms. We also use team tasks. You've seen data from strangers and loved ones in dyadic interactions. We're now expanding our dyadic research to psychotherapy research. We've studied parent-child interactions in low SES and bilingual communities. And finally, we've also begun studying autism spectrum disorder. And specifically, we worked with the Sackler Institute and with Northwestern University to record EEG and video data from adult-child dyads. And this illustrates how social behavior and different tasks and the different social partner might influence synchrony. So we compared kids with autism spectrum disorder to typically developing kids as they are engaging with their parent and an unfamiliar adult like a clinician. And during each of these interactions, they're either playing with a toy, object engagement, or there is no toy and they engage directly with each other, human to human, so to speak. And what we see in this pilot data is that both mutual gaze and synchrony is increased when the toy is removed from the equation, so when there is real social engagement. And what's important is that this increase is stronger for caregiver-based interactions than for interactions with unfamiliar adults. And it is also stronger for typically developing than for autistic kids. And so what these pilot data drive home, and this has been mentioned, I'm sure, throughout the day, is that you might want to study social disorders in a social context because it matters who you talk to, what you do, and it also matters who you are. And with respect to the latter, some of it might not even be driven by the social contexts. As I've already mentioned, differences in or individual variation in neural architecture, like brain structure or oscillatory patterns, might indirectly influence synchrony devoid from social reasons. Now, the next step then, logical step, might be to link our neurofeedback work with our autism work and try to see if a hyperscanning neurofeedback intervention can actually improve social communication in ASD. And like this, builds on the narrative that we saw in the mutual wave machine, where those people who are motivated through a neurofeedback environment also show an increase in synchrony. We know that kids with autism are attracted to computer-based social interventions. Now, to stick with our neurofeedback here, we've also expanded that side of our work to group-based synchrony, where synchrony is visualized as an evolving social network. So here you can see how the brain activity of 6 people is translated into this evolving network where some people are outliers and some people end up being hubs. And so that very intuitively raises the question on whether you want to be a hub, are you a leader or a follower, or if you want to be one of those independent outliers that might be going their own way. And so we've thrown those types of questions into groups of participants who are invited to engage with the social network dictated by their brain synchrony and with each other through joint action, essentially creating a composition together. And we've also started working with dancers, specifically the dance group ICK Amsterdam, who has been working with notions of synchrony for a while. And we've met in several workshops that culminated in a research/performance at the Ballet National de Marseille last year, where 2 dancers performed in an audio-visual dialogue with their own motion synchrony, as well as interbrain synchrony between either the dancers or the audience. So here you can see that the flows are pulled together to the center when synchrony increases and pulled away when synchrony decreases. Another outcome of our conversation with the dancers is that we've tried to develop a taxonomy or a common vocabulary of synchrony, focusing on the forms by which synchrony can be achieved. So notions like simultaneity and togetherness are super intuitive, but they're really difficult for dancers to do on cue, right? They can't just do something simultaneous but not together, and vice versa. And similarly, in our neuroscience community, we're grappling with the distinction of whether synchrony is meaningful because things are done at the same time or because they're performed together. We looked at synchrony units, so synchronizing bodies to each other, but also the performer and the audience. And then, of course, different limbs in our bodies are also synchronizing or desynchronizing to each other. And vehicles of synchrony, anticipation and resonance, tuning and feedback, shared attention. And then we can ask whether these types of constructs, which are psychologically, intuitively meaningful, might also map onto different interbrain synchrony metrics in a meaningful way. So to illustrate this, let's go back to the mutual wave machine, where we saw that there's a consistent pattern where some behavior or personality factors either projected power correlations at 8 Hertz or imaginary coherence at 20 Hertz. And interestingly, we see that the two co-modulate. So pairs who show higher projected power correlation at 8 Hertz also show higher imaginary coherence at 20 Hertz. And so one way to think about this type of finding is in terms of attentional fluctuations. So I come into an interaction and I'm not going to be fully attentive for this 10 minutes straight. It's just not going to happen. Instead, I'm going to have moments where I'm more attentive and moments where I'm less attentive. And the same is true for the person I'm interacting with. And now, the more those attentional fluctuations coincide, the more moments or windows of opportunity there are to actually build a common ground and shared representations, which are arguably indexed by beta phase. And now we've recently developed hyperscanning Python pipeline, HyPipe, where you can also try to compare or explore different types of synchrony metrics depending on your research question and hypothesis. And so this is spearheaded by Guillaume Dumas, who I see is hiding behind my face. You'll see his face in a little bit when he gives his lecture, but here he is. And other people who have been developing this include Florence and Anaëlle and Phoebe. And what it does is you can either use the pipeline to pre-process your data, or you can load pre-processed data. It merges your data sets. We have implemented different types of intra and interbrain connectivity metrics, and we continue expanding on those metrics, and also continue on trying to figure out ways in which they map to psychological constructs. And you can visualize your results shown on the bottom right. And you are all invited to contribute. It's an open source project that lives on GitHub. For example, Yafen Pang, as well as Nigel Janssens and Sasha Key have already contributed valuable comments that have stirred improvements and changes to the pipeline. And so I wanted to close with emphasizing the role of the community in any and all of our research, and showing the faces of all the people who have contributed to these different projects. And these are not even all of my collaborators. They don't fit on this slide. And then we're also supported by different kinds of funding agencies, both from the sciences and the arts in different countries. So thank you for listening, and I welcome questions.